Hello and welcome to this session from cloud to on-prem capacity planning and CPU analysis. My name is Matt Bichelle, Senior Director of Product and Solutions Marketing at Aerospike. It's my pleasure to introduce Albert Autin, System Engineer at the Trade Desk. Albert's been with the Trade Desk almost 2 years, but has actually worked with Aerospike a number of years, even before working at Trade Desk. And I might remind people that the Trade Desk is actually the world's largest independent programmatic advertising DSP, and also that this is not Albert's first Aerospike Summit presentation. 2 years ago, he gave a session on large-scale cluster management with Ansible. I want to encourage people to ask questions and put it in the chat, and we'll have a Q&A with Albert after. So I don't want to steal any of Albert's thunder. So with that, Albert, take it away.
Hi, everyone. My name is Albert Autin. I'm happy to be here with you all today. I want to tell a story about our migration from cloud to on-prem for one of our largest Aerospike clusters. Along with that, some interesting findings and methods we use to gain confidence in the move. I've been an engineer with the Trade Desk for almost 3 years now, and I've been working with Aerospike for 6 years. I work with Aerospike every day, helping to manage nearly 700 systems across the globe for the Trade Desk. The Trade Desk is a technology company that helps connect advertisers to the consumers they want to serve ads to. In order to serve that need, we store marketing data and use that data to select which advertisers' ad to show. To preserve website performance, we have a limited amount of time to figure out if we want to try to buy a user's impression and how much we should pay for it. We also have to do this 12 million times a second. In early 2021, because of a new business requirement, we decided we wanted to move this cluster off of AWS and into one of our own sites. The reason we chose to support this in our own site as opposed to another cloud provider is because we could tailor build the solution to suit our needs. It's also difficult to migrate away from AWS because the great variety of offerings they have. At first, I tried convincing the VP of engineering to just dive in head first on the first build that we could come up with, but he didn't bite. We had to run a POC and prove out we know what we're doing and measure where we stand right now, what bottlenecks we have, what problems we have. So we want to run a POC. Instead of waiting months for hardware to arrive, we'll borrow some of the systems we're running Aerospike on right now from our bidding cluster and compare the performance. This table on the screen here shows how the specs stack up against our existing AWS machines. Already our suspicion was that we wouldn't have enough CPU power. 96 threads at 2.5 gigahertz versus 80 threads at 2.1 gigahertz. That's around 30% less CPU power. Everything else looks great on paper. More storage, more IO, more RAM, but the CPU might bite us. Why do we care about CPU? We use Aerospike's complex data types within this cluster, specifically map objects. This offloads the logic of dealing with a large dictionary onto Aerospike, so we can do quick, simple operations like add this new interest to this record. We also use compression. Compression reduces the amount of disk IO, network IO, and disk storage needed in this use case by almost 80%. So CPU is important. On to the POC. To start off with, let's talk about the POC and why we set it up the way we did. I want to go through some setup considerations. Number one, we should have more than one node. Replication should be included in any of our simulations, and this changes the way the system behaves. We intend to use replication in our production use case, so we should test with it. Number two, we should use a control cluster and a test cluster. This will make it so that any workload we mirror between the two can be directly compared. Instead of worrying if our sampling logic is off or anything and the test is wrong, we'll be able to compare apples to apples if both get the same workload. Number three is backfill. This is pretty important because the amount of work required to update a record on Aerospike, especially with CDTs, goes up as the record size increases. For example, adding one element to an empty map is pretty easy. Adding one element to a map with 100,000 entries is a bit more work. CPU and IO needs increase with the record size, so backfilling this is important. Number 4 is that streaming updates must match the backfilled records. This ensures updates are occurring to the larger backfilled records and not just creating new records. So with all these things out of the way, we ended up with a control cluster and a test cluster. The control cluster is running off the same AWS hardware you use today, 4 M5D metal machines, and the test is running on the 4 stock machines we borrowed from our bidding cluster. We can start inspecting performance and comparing. The plan to characterize the system performance was to keep ramping up the traffic until the cluster couldn't take anymore, and then compare numbers. The hypothesis was that the control systems would push back because of disk IO, and the test on-prem machines would push back because of CPU limits. We were right. The control cluster started pushing back because it couldn't flush data to disk fast enough. We can see that reflected with high IO wait times and PSI, and then high write queue depths and disk overload errors in Aerospike. The on-prem cluster began slowing down because it was out of CPU. We could see load averages over 400 in some cases. Disk, network, and other resources looked fine, but CPU was an issue. We can see using PSI, the amount of time the kernel spent waiting on resources in these charts. The test cluster is hardly ever waiting for IO at 3%, versus the control cluster waiting for IO 25% of the time on average. The test cluster is also showing a flat line for CPU waits at 70%. This means that 70% of the time a task spins in its queue is just waiting on CPU resources. These first 2 charts here using Facebook's PSI metrics, these are all available within the 5x and higher Linux kernel. Below these 2 charts is load average. Both are good indications of bottlenecks, but not really the most granular we can get. Since we think CPU is our bottleneck for these on-prem clusters, let's talk about measuring the CPU bottleneck. There are a few things in our toolkit we use day to day, usually found in our Prometheus graphs, that we use to find these issues. Again, Facebook's PSI metric I mentioned earlier today, this is very helpful in determining what your bottleneck is and how bad it's contributing to the queue time within the system. They have indicators around CPU, IO, and memory, so you can pinpoint which resource you're lacking. Number 2 is load average. This just shows the amount of tasks that we have queued or blocked, waiting for some resource. High load average doesn't really tell us much other than that the system is at its limit when its value is much higher than the core count. And these are good starting points, but we know we have a CPU bottleneck, so what do we do about it? Enter flame graphs. We decided that inspecting the distribution of where CPU cycles were spent would be very good. There's a tool that you can install Linux called perf. Perf can sample and track CPU time spent in certain methods of running applications. I'm definitely not an expert using perf, it's still new to me, but I know it works very well with programs written in C, which Aerospike happens to be written in. So using something similar to the commands on this slide, we were able to take a sample of the CPU Aerospike is using. Then we can take that recording and generate a flame graph. Flame graphs are a really hot way to visualize CPU cycles for performance analysis. Let's talk through interpreting this graph quickly. The x-axis here can be seen as the amount of CPU cycles spent in the function. For example, SSD write here and all of its children take 17% of the CPU power, as shown in these green brackets. If we look closer at these 17% CPU usage in that function, it looks like it's actually mostly due to Z standard. And that's shown higher up the call graph. So the y-axis here is the stack depth. So SSD write In green brackets is calling SSD write bins, which calls SSD buffer bins, and so forth. Great. So now that we have all this information showing us where our CPU is going, what we did is we iterated through all of these items in the flame graph and considered if we can tune anything to make it faster. Maybe changing the sprig count would help. Maybe a different compression library, and so on. We didn't find any easy wins, except as we iterated through each of these CPU consumers in the flame graph, one that really stuck out to us was map add items. This is when we want to pass an element to Aerospike to insert into a dictionary. It's taking 25% of our CPU power. But this isn't just adding items, it's also doing a cleanup we have. Remove by value. That's contributing to 17% of the total CPU time. In our current deployment, that means remove by value is taking the equivalent of 2,500 cores of CPU power, which is not insignificant. The remove by value is necessary in our use case, and we made it tunable. I want to explain a little bit about our data structure. While we do have a record level TTL in Aerospike, on each record, we also want to indicate how long an entry in that map should live for. Some targeting data should be short-lived, and some can hang around for a very long time. So our data structure is as follows. For a specific device ID as the key, we want a map or a dictionary of targeting IDs. And for each targeting ID, it must have some expiration date. We represent the expiration date as a custom epoch timestamp and perform a remove by value with a range of epochs start to now. This example is just shown with regular epoch time for ease of reading, but in our production use case, it has much lower resolution. We nest all operations together when working with the key. When we want to update a key, we'll maybe add 10 items, then remove by value some percentage of the time, all of one operation. This keeps it efficient. What we expected is some random chance to have this remove by value range operation added to our list of operations. But when we try to tune this percentage for this thing to be added to our list, the CPU usage didn't budge. So we tried lowering it more. It didn't move at all. We tried setting the chance to add remove by value to 0%, which should be disabled. But still, we looked at our flame graphs and the CPU usage for remove by value didn't budge. We had a bug. This bug made it so that we performed the remove by value cleanup 100% of the time. That meant every time we wrote a record, we made Aerospike traverse all the values in the map, which could be many thousands, and attempt to clean up. This was because the randomness function that should have been evaluating if we wanted to add this was not thread safe, where when we rolled the dice, it always came out to true. This was just a couple of lines of code to fix and had a big impact. Since we had such good luck with measuring CPU cycles from the CDT bug, and the throughput we expected from perf was very true to how much throughput we gained, we wanted to see what else we could find. One thing that Aerospike turned us onto was K ordering or key ordering. There is a way to make Aerospike store your dictionaries in a sorted way rather than unsorted. They told us using the magic of math that it would surely be more efficient. We were using unordered maps because it's the default and we didn't put much thought into it. Since a map or a dictionary ensures that you don't have duplicate entries within it, every insertion will force it to traverse through all entries. So we get an efficiency of n shown on this table. Storing this as a sorted key map instead allows insertions to be much more efficient at log of n, where n is the number of elements within the map. I lifted this table from an article on Aerospike's website where they publish worst case scenario efficiencies of operations. And here's the link to look it up. So this is a great suggestion. It looks great on paper. It turns out this change can actually change which object gets returned to the consuming applications, at least in C#. A sorted dictionary type is returned instead of a generic dictionary type, which means we have to be careful. We need to ask all of our consumers to switch over. We have to test all the consumers. It could be a lot of work. Is it even worth it? So that's the theory. On to the real world. Knowing how changes will affect your performance is hard, especially at scale. Since we have this wonderful POC setup already, we'll just use that same set of systems to perform a test to compare if k-ordering helps. We'll have the control continue to use unordered maps, and on the test cluster, we'll use sorted maps. There was a little bit of preparation required in that we had to switch in the application to use ordered maps, had to be added in. And additionally, we had to pre-sort all of the records using a background operation. We wanted to know the steady state, how much CPU cost was there, as opposed to the cost of converting unordered to ordered and insertion. So we had to prepare it first. Here's the comparison. This is comparing two of the same type systems over a 24-hour period under heavy load. In the control, we're spending 28.7% of the time in CDT, but only 12% using k-ordered maps. This means we can probably reduce our overall CPU needs by 16% just using k-ordering. And since CPU is our bottleneck for our on-prem systems, this means we can go 16% faster or have 16% less hardware. Thanks, Aerospike. So fixing the bug bought us the ability to tune this correctly with the remove by value and significantly reduce our CPU needs for the on-prem site. Then we found we could gain another optimization by enabling ordered maps. That bought us another 16% more CPU savings, again, measured using perf. And finally, we noticed we didn't have turbo mode enabled for the on-prem POC machines, which netted us even more power just by flipping a switch on for the CPU. Originally, our AWS to on-prem comparison looked a little bit grim. The M5D metal machines outperformed our on-prem clusters by 30%. But with all the improvements we made, the on-prem machines were actually running about 30% faster than the AWS M5D metal machines. This led us to our final capacity recommendation, and all the improvements we found ultimately led to over $1 million in savings. For anyone curious, this is the final build spec we landed on for building the cluster out on-prem. We decided to go bigger on CPU anyways, since that will still be our main bottleneck. This will make sure that we have plenty of room to grow. That's it. Thank you.
Thanks, Albert. That was a great walkthrough of this, what I would describe as a fairly unique scenario. I would say that most customers consider the opposite, going from on-prem into the cloud versus the other way around. But obviously, a customer need is there. One thing I wanted to ask you about was the workload. You said that you had borrowed machines from your bidding cluster. Are you allowed to kind of comment what the workload was for this test case?
This test case was our cold storage cluster, so it's much heavier in terms of I/O and CPU. The objects are larger; they're up to 1 megabyte in size, and we use all those extra features, CDT and compression. So that's the main difference, is it's heavier, whereas our bidding cluster is forced to be lighter weight because we have to shrink down the object size, make sure that we can serve ads in a very performant way.
And so is that part of the supposition that up front you're going to say, hey, we've got these bidding cluster machines that are used to lighter weight or smaller objects, maybe no compression, that they might limit out on CPU. Is that kind of what went into that upfront belief?
Yeah.
Okay. And so the next question is kind of curious, because a lot of customers, a lot of prospects, they do, they either want testing or they want a proof of concept. Aerospike, we do our own benchmarking as well. And so the question really I'm getting to is, how did you simulate or the workload, or how were you able to do that? Was it a forked real live workload, or what? How was that? How did you arrive at that?
Yeah, that was something I skipped over a little quick on the setup considerations for the POC. Is we're actually sampling our production traffic based off of some modulus on the digest, and then shipping those same requests to both the POC cluster and the control cluster. But it is real production traffic.
Okay, awesome. So I know your presentation didn't necessarily cover architectural considerations up front. Obviously, this is handling streaming information, or streaming updates. So I'm kind of curious, based on your experience, and you are quite an experienced Aerospike operator, how does the trade desk handle or manage streaming today? Is there a connector or another open source tool that you're using? Just tell us a little bit about that.
It really depends on the use case. For some of our workloads, we try to do live updates, but depending on the classification of the data, some data can be allowed to be queued for longer than some data, but we try to get in as quick as possible, of course. Current streaming technologies, we're actually looking into Kafka and maybe some ways to improve what we're doing right now. Right now, we're just mostly shipping big chunks of data to S3 and then processing that using S3 notification system.
So that might change a little bit, if you're on-prem, I guess. Is that to be determined, or what's the status then?
We'll have lots of egress costs. That's the plan right now. But yeah, like I said, we are looking at a different technology. The big problem with this stack right now is we don't have user affinity. So updates for the same key may come in thousands of files from different servers across the world, which hurts us because we can group all these operations to write a record. We can batch all those writes together, but if we had if those are split up across many machines and many files, then we don't get that efficiency gain. So we have to write the record 1,000 times a day instead of 100 times a day. So we really need to get better at user affinity, I think.
Fair enough. Given that this is for ultimately a cold store workload, does this mean then that even though these machines will be on-prem, that it needs to communicate with other cloud providers or other regions, I guess?
Yeah, this is kind of our system of record. So this cluster will be the source of data for, I believe, all of our edge clusters. There might be some special cases, but there will be communication to all the other clusters. We'll use a custom system that will transfer the data that's relevant out of the system of record into the edge systems. So we have some thaw cycle where users will constantly be thawed or based off some trigger. And then there's a system that's co-located with that Aerospike cluster that will fetch the data and then purge out stuff that's not immediately relevant and then ship that to the edge cluster.
Okay, yeah, makes sense. You only want to ship efficiently, if you will. Was there an SLA, or is there an SLA that you can talk about that shipping from the cold store to the edge clusters, and does it vary, I guess?
Yeah, a lot of the data still comes through a live path, especially if it's latency sensitive. So it will be immediately propagated to relevant DCs. On the non-live path, it's usually more bulky. Data providers will send us data. And they only go through the cold storage thaw cycle, and that happens on a 7-day cadence. So it'll take 7 days to 100% thaw out every single user worldwide.
Yeah, that makes sense for sure. There are a couple of things that you discussed that I thought were fairly unique, or at least not that common. I don't know if this is a throwaway question, but the type of, I liked when you said, flame analysis was very hot on CPU. Is there, in your experience, is there something analogous or an analogous tool that you've used for other diagnosing or other problems, so versus CPU, maybe the IO issues or not the IO, I'll say, yeah, issues on the existing systems that you've used that you like, I guess. Could you comment on those?
Yeah, so the main things that we're worried about with setting up an Aerospike cluster is mainly going to be the IO. For most clusters, we're not very CPU dependent or even network dependent. So IO is usually our top priority. We use Aerospike certification tool to test drives for that. We've ran those across a wide variety of hardware. So that's part of the reason why we weren't even looking at IO, is because we've already tested these hard drives and we know what they look like, and we know what the hard drives look like on AWS and all the systems that we're considering. So it's fairly straightforward to figure out if we have enough IO, because we've already tested and documented what we know these systems can support as far as drive IO. After that, ignoring CPU, there's network. And that's usually a pretty straightforward formula. You have a 25 gig NIC. You can take your object size and how often you transact with it and come up with your data rate and figure out if it'll fit.
Some math, yeah. Yeah, no, it makes sense. Given the workload is the cold store is a little bit unique. And something else that you talked about, or again, maybe is a little less common in Aerospike, is K ordering for maps. It certainly is very logical as you explained it for this use case, but is the trade desk going to consider it, or do you guys find utility in it, maybe in some of the edge use cases?
We have, we've been using Aerospike for a long time. I think 9 years or something like that at the trade desk. It's been ingrained in the trade desk for a while. So we're not in a hurry to migrate any of our big existing use cases over to CDT. CDT is relatively young compared to that. I think they were released, 2 or 3 years ago? No, it's been more now. 4? I can't remember. Anyways, we have works. We're using protobus serialized objects for our edge clusters, and that works really well. And we're just not, we don't have the appetite to go through and change our data structures right now. But for new use cases, yes, definitely. And if some of the ideas I'm pitching go forward, then that might happen for the edge case as well. But we'll see.
All right. So I guess I'll kind of conclude. I guess you mentioned this is half a comment and half a question. Just, how do you foresee the ultimate migration going?
I'm pretty sure we over-engineered it. We're planning for worst case scenario plus 20% and plus 10% there. And so I think it'll go pretty smoothly.
All right. Well, I've no doubts, given you and your teams and the trade desk entire team experience with us. So with that, thanks again, Albert. Yet another summit session for Aerospike. So we do appreciate it. And if you'd be open to receiving questions, again, this is a pretty unique in a good way use case or test case. So thank you. And I think with that, everyone, I will close the session and encourage you to enjoy the break in the agenda. and visit some of the booths. And again, feel free to reach out to Albert. Thanks, everyone.